So now let's turn towards the next presentation, and let me introduce the authors. So the first one will be Dr. Friedrich Wiemer. He is a senior security expert at Bosch, specializing in secure communication for in-vehicle network. He is currently focused on pre-development activity, architectural design, and innovation in cross-domain use. Focused on symmetric cryptography during its PhD in mathematics, he still actively contributes to several standardization efforts, such as Open Alliance TC17. In addition of that, he is CEO and co-founder of Crypto Solutions Company and published numerous papers on cryptography and security. We also have another presenter, which is Nils, Heitmann, a specialist in automotive Ethernet application at NXP. His work is focused on Ethernet switch technology with a dedication to both current and next generation of automotive systems. You can go then.
Thank you for the introduction. So let me see how this works here. Yeah, so we want to talk about measurements for the MACsec key agreement that we conducted. So we conducted a simulation and some measurements and talk about what actually the key agreement time is that we can achieve in an automotive software stack. So to understand this, I want to spend some time and talk about what MACsec and MKA actually is and how MKA works, so that you can hopefully also follow our investigations and what we find. We then talk about the initial setup which we used to come up with our motivation why we wanted to look into this, the things that we did for the simulation, and then also Nils will take over the last part where he talks about the demonstrator that we use from NXP to validate our simulation results here. Okay, so probably you've heard about MACsec because everyone is talking about it. It's actually quite an old security protocol, by now almost 20 years old, or 20 years specified in the IEEE. And it provides integrity, authenticity, and confidentiality for our layer 2 Ethernet frames. And if we look at what MACsec is, it's actually more than only the data plane protocol for protecting the Ethernet communication. It actually consists out of 3 steps, and it talks about the security guarantees it can ensure inside one MACsec group, which is called this connectivity association here. It all starts with an authentication step, so the participants that want to talk to each other in a secure way authenticates belonging to this connectivity association, which in automotive setups is typically done by pre-sharing keys, for example, in the vehicle assembly. Then we have the key agreement step, which is done every power cycle and maybe even more, depending on how much traffic there is, which takes the initial long-term key, the CAK, to protect its own messages. And then within this MKA, there's a session key negotiated. This is this SAK. And finally, this SAK is used in MACsec itself to do the actual cryptographic protection of the Ethernet frames. So while this talk is about MKA and the timing behavior of MKA, this is what we want to focus on. And I want to give a more detailed look into how MKA works in this slide, basically. So we have here, for this example, 2 participants, Alice and Bob, which want to talk to each other and negotiate a key for MACsec usage. So they start both when powering up their MKA component by choosing a random member identifier. This is used to identify themselves in this MKA run, and this will be newly randomly generated each time they restart their MKA run. Then MKA sends periodically messages, and in this example here, Alice starts sending its first MK PDU, which consists of this member identifier saying, okay, this is actually a message from Alice, from myself, and it contains a message number, which is basically a freshness value and is counted up for each new message that Alice sends. Then this also contains a key server flag and says, okay, Alice can act as a key server, and she will do so with a priority of 200. So then Bob receives this message and says, okay, I actually also want to be the key server, and I want to do this with priority 100. So a lower value means a higher priority. At this point, Alice knows, okay, there's actually another person here I'm talking to, this is Bob, and Bob also wants to be the key server, so she then in her next message sends, then because she sees that Bob's priority is higher than herself's, she says now, I don't want to be the key server anymore, go ahead Bob, or go ahead member identifier 42, you will be the key server. And this conducts the first part of the MKA run, which is the key server election, which consists of these 3 messages here. Now the MKA key agreement actually sends more than these basic parameter sets. And one further information that is used for the next step is this potential peer list. Here, when Bob receives the message from Alice, he knows that there is a potential live peer because he has not seen this member identifier 1337 before. So he adds this member identifier together with the message number from the last message he saw from that member identifier to his potential peer list and sends this over to the other MKA participants. He is not yet sure that this is actually a live peer because this message could also be a replayed message from a previous run. Now Alice actually receives also this potential peer list and see, there's actually a reference to my own member identifier in it. So I now know that Bob has received my message and that Bob is acting in a live fashion to the messages I have sent. And this is the reason why Alice now adds Bob to her own live peer list, indicating that she is ensured that Bob acts live in this MKA run. And then as a last message of this liveliness determination part, Bob now also received a recent indication of himself in the message by Alice. So he also knows that Alice is acting live in this key agreement phase. So Bob now transfers Alice from his potential peer list to the live peer list. Because Bob also knows that he's the key server, he can also send more information, namely he can actually choose an SAK, a session key, encrypt it and send it in this distribute SAK parameter set. So sending the key to Alice to be used, and he also adds the information that he himself is able to use this SAK from this point in time on now. And then Alice finalizes the key agreement by sending, decrypting the key, providing it to her MACsec implementation, and then sending Bob the parameter set, okay, I am also now able to use this key. And from that point in time on, they both know they were able to use the key for conducting MACsec, and they can actually start their MACsec communication. Typically, in the normal IEEE standard, these messages are sent cyclically with a fixed period of time. So you see that there are 5 messages required in this case here. So if you send this every second or every 2 seconds, then this whole process takes a lot of time. Yeah? This is why Open Alliance TC17 looked into optimizations. And the key optimizations they suggested in this specification, in this first version of the specification for switched Ethernet, is that we actually fix the key server election by fixing the priorities and the key server flag. Yeah? From that point on, the MKA optimized implementations can assume that they already know who will be the key server. Yeah? They know their own role in this MKA run. They also said that if I receive an MKA message that changes my internal state, I immediately respond to this and do not wait for the next cyclic sending of this message from the MK, from this MK hello timer. And they also added some hello time ramp up phase. So you can think about this when I start my MKA stack. Initially, I send many of these messages, each time waiting a bit longer for this cycle until I reach the final cycle time I want to send these messages on. And the idea here is to hit the time when the other component is also powering up its MKA status quite tightly so that we can start with this key exchange message without waiting too long. Okay, now that we know how MKA works, I show you briefly our initial test setup. This was based on 2 Raspberry Pis with a Linux implementation for MACsec and for MKA. And we used this to understand, first to compare 2 different implementations of MKA, and then also to understand how these MKA messages work and what kind of observations we can do here. So the results are, I don't want to go too much into the details because we want to cover the actual simulation and measurements results in more time. What we briefly saw is that the normal WPA supplicant implementation of MKA takes quite long, so 2.5 seconds, while there's an open source implementation for the automotive optimizations from technical engineering available on GitHub called this MKA daemon. This is very much faster. And now it's still running on a Linux, on a Raspberry Pi, so not a real optimized embedded system. But we see that the optimizations bring us somewhere. Yeah? However, what we realized when we looked into the traces is what I want to explain you now. And for this, we again look into this message exchange that we can observe here. So assume in this first example that the key server starts first. And bear with me now, the key server is Alice and not Bob anymore. Yeah? So here, Alice starts first. This means after some start offset, the MKA component is up and running and can send messages. So it starts with this hello ramp up time to send these MK PDUs out, and is basically waiting for responses, which there are none yet because Bob is still starting up its MKA component. After a bigger start offset, Bob also starts. The MKA component of Bob is also available and now starts also sending messages. And from this point in time on, this immediate response thing happens. So Alice responds to Bob message, Bob responds again, and so on until Alice distributes the key here and Bob responds to the key being received and being available for MACsec. So this is what we define. The key agreement time is from the point in time where the latest peer sends its first message, so when the peers actually can communicate with each other, until the time that the last peer acknowledges that it can use the SAK, the key to be used. Yeah? Now let's have a look at the opposite situation where the key server starts second. So in this case, Bob starts first sending messages. Alice, after some time, also is able to send messages. And again, beginning on the first message of Alice, Bob starts with his immediate responses. And here we can see now that the second message Alice sends actually contains already Bob in her live peer list, because with the first message of Bob, she got the reference to herself, so that she knows that Bob is actually a live peer, and then she can directly distribute the SAK. So in the end, if we look again, what is the key agreement time here from the first message of Alice this time until Bob again acknowledges the SAK to be used, and we count the messages, then we see on the left side we have 5 messages, while on the right side we have 4 messages. So this was the initial idea for the simulation, that we should see different time to key agreements based on which of the nodes starts first. Now, before we can look into what we actually simulate, let's have another look at what actually happens with an AutoSAR-based software architecture. So in AutoSAR, we are not directly handling the received frames and are reacting to it, but actually the message handlers that are doing this are called in a cyclic or periodic way. So we have a specific timing where these message handlers are executed, and then the messages are actually only sent out. So again, looking at this traffic picture you know very well, what happens is Alice starts at some time, and now these dashed lines here indicate when the message handler of Alice is called and when the message handler of Bob is called. And now, after each of such a dashed line, there can be a message sent out. Based on the hello ramp-up time, maybe it's not actually done. When at the time when Bob starts up and receives the message from Alice, he will actually respond to that after the next time when this message handler was called. And this continues and continues. So this will already delay the messages after the next call of the message handler. So we would expect that if we implement this cyclic handling of the messages, that we again see longer time to key agreements. Another thing that we will observe is that the cycles where the message handlers are called are not totally aligned, so they differ. And this difference might have actually an influence on the time to key agreement as well. And the last thing I want to mention here is that, of course, message processing takes some time. So the message is not directly sent when the message handler is called, but with a slight offset here. Okay, let's look into the actual implementation for the simulation. What we did, we developed an MKA plugin for the real-time AdWord Pegasus simulation tool. And for this, we assumed that the time it takes to process a message takes roughly 1 millisecond, that there's a specific delay to install keys in your MACsec implementation. So this will be an additional delay before you can send this SAK use parameter. The starting offsets for the nodes are chosen uniformly distributed at random between 0 and 100 milliseconds. So this means the difference between the client and the server will be between minus and plus 100 milliseconds. We are looking at a switched network configuration with a hop-by-hop configuration of MACsec. So this complies to the TC17 MKA profile for switched networks. And we are looking, simulating message processing cycles, between 1 and 10 milliseconds. And this hello ramp-up, time ramp-up value is 20 milliseconds. So we start with 20 milliseconds delay between the first two MKPDUs, then go to 40, 80 milliseconds, and so on. Okay, so you already have seen this, a glimpse on the results here. So let's take a moment to understand what we actually see here. We have different plots, 10 plots for each processing cycle, one plot, 1 milliseconds, 2, 3, and so on, until 10 milliseconds. We see the 30 milliseconds time to key agreement goal from Open Alliance here in the light green area. So this is what we want to hit. And each of the dots correspond to one run of the simulation, which was on the last slide. I didn't say it. We run 1,000 runs per setup here. So you see also that we only look at 20 milliseconds to minus plus 2, minus till plus 20 milliseconds. So this is an excerpt, and on the next slide you will see a full picture. And yeah, if we look at the results here, we can, I think, see already two different things here. One is that with on the positive part of the x-axis, time is always faster than on the negative part of the x-axis. So this corresponds to the scenario where the key server starts first or second. So if the key server starts first, if the offset of the key server is smaller, so the difference is then negative. And we can see that it's always the case that the left half of the plot shows bigger numbers than the right half of the plot. And we can also see that there are like 3 different classes of time we are hitting here. So that's maybe something we need to look into as well. And then we see in general that in the simulation for 5 milliseconds processing cycles, we still always reach the 30 milliseconds goal of TC17, while after that we can also not ensure that it's always be this 30 milliseconds. Now I promise to give you this bigger picture here as well. So here we see the full simulation run. At the edges it gets a bit thinner because statistically there are less data in there. So let's look more into the center. What's also already visible, but Nils will look into this in more detail in a second, is that there is a specific cyclic behavior. So you can see this here. This has a 10 milliseconds processing time. So if you look at the point in time from 0 milliseconds to 10 milliseconds and from 10 to 20 milliseconds, the dots looks very similar. Yeah? So actually we see a cyclic behavior that is based on the message processing cycle here, which also makes sense that the actual difference that matters is the difference within the processing cycles between the two nodes and not the actual offset of, I don't know, 100 milliseconds minus 27 milliseconds or so. Okay, now I hand over to Nils, and he will look into the actual measurements that we did.
Yeah, okay, thank you, Friedrich. Yeah, we all like simulations, but of course, doing some real-world measurements is also nice. So yeah, we thought we should confirm what we found in simulation, if that actually links to some real-world behavior. So we came up with this test setup. We can see 2 automotive MCUs. They run the MKA stack. So two peers, one is server, one is client. They're connected via a 1000-base T1 link with a switch in between, and we use this switch via a control laptop to actually control the experiment. So the laptop will send what we call in this experiment a sync frame to both the key server and the key client. This contains the starting offset that you remember from the last slides, that we are able to control which will start up first and second. And with that, the local client will start a local timer, wait for the offset, and then start the cyclic processing. The processing is an MKA implementation, having all the TC17 profile implemented, including HSM support locally. And while this is not a full AutoSAR implementation, this mimics the cyclic message processing, where you retrieve Ethernet frames that you received, then process them in your MKA stack, run your state machines, and so on, and then egress a response if necessary. Yeah, so we did this run. Let's have a look at the first results. So this is again the plot going from -20 milliseconds to plus millisecond starting offset. And what we can also immediately see is that we can confirm for the key server start second, the average time to key agreement is lower as for key server starts first. So that is more or less confirmed. What we also see, especially for the 10 milliseconds, it's very clear to see that you have certain groups of key agreement times. So in certain situations, the key agreement takes much longer compared to other offset combinations. So if you look in the middle, when both start up almost exactly at the same time and have this 10 millisecond cycle time, the key agreement is more than 50 milliseconds. And it is much less if you have them offset. And if you think about the messages, that actually makes sense. We also ran it once for the what we call IRQ on these slides. So there's no delay, and just run the execution of the MKA stack as fast as possible with no delay in between. And then we also reach this limit. So let's have a look at the full data. Again, from -100 milliseconds to plus 100 milliseconds. And here we can see almost the same repeating pattern for key server starts second and key server starts first. So even with these ramps for the key server starts first, we can observe that here. So it looks to be that our simulation was pretty good and pretty close to this one real experimental implementation. But you might be wondering, didn't Friedrich just tell us 5 milliseconds is enough? Why is this well above 5 milliseconds? Yeah, we also wondered that, and we looked into what the problem is here. And it turns out not just the cycle time is important, but Friedrich also mentioned that we also have to take into account the processing time, the time it takes to ingress a frame that you received, process it, and update your state machine of MKA and so on, and egress it again. That is actually in this demonstrator quite significant amount of time. And if we actually update that parameter in our simulation, we can kind of match that. So what you are seeing here, in blue, it's a 10 millisecond experiment you have seen in the last slide. That's the blue data, and every plot is the same blue data from the experimental. And then we reran the simulation, again also for the 10 millisecond cycle time, but this time adding a processing delay of 1 millisecond, 3 milliseconds, and 5 milliseconds. And now we can see, okay, this matches much better, especially for the 3 milliseconds. This is very close matchup to what we see with the experimental results. So it would be, at least in our simulation setup, 2 parameters, the cycle time plus the processing time. Yeah, again, scaling this up to the full view. So this is the experimental data for 5 milliseconds again and 10 milliseconds. And now the simulation also run with a 3 millisecond processing time. And you can see, yeah, it's matching up quite well. The simulation is pretty close to our experimental setup. And yeah, we are at this point quite happy with it. I mean, we could have probably optimized more to make it match really close, but in the end, we have to remember that our experimental setup is just one setup and also not representative for all implementation. So we call this yeah, close enough for now. And basically, this will just confirm that our simulation is good approximation here. And with that, I would like to jump to the conclusion of our talk. And is it there? Yeah. And one is, of course, I mean, reaching 30 milliseconds, you have seen this for the experimental implementation. That is not going to happen just by itself. You actually need to take care that you achieve that. So there are some, you need to be careful to do that. Then the observation that fastest key agreement time happens when the key server starts late. We think it's a bit unintuitive, but I think Friedrich explained quite well why that happens. So that makes sense. It's just an observation here. Next is the hello time that has been defined in TC17. The profile does not matter in the default case. So in the simulation and also in our experimental results, the hello ramp-up time does not do anything. So with this setup where we have one starting up first, sending out messages, and the other is not there yet, the messages will just go into the empty void and are lost. So there's nothing happening at that point. And only when this second peer is online, it will immediately start as a first action sending out a frame, like the first MKA frame. And this will then, of course, immediately be received and responded by the other side. So in all these cases, the hello ramp-up time has no impact. Then what we've also seen, like a small variance in different startup time can have a huge impact on the overall time to key agreement. So if you are validating your implementation, then maybe also make sure that you have some jitter in your experiments to actually see, do I land maybe somewhere where it takes much longer to have key agreement and not just stick to one very tight setup. And then, the implementation hint, cycle times need to be very small. So it needs to be less than 5 milliseconds to actually achieve the key agreement time of 30 milliseconds. And then what we also mentioned, the processing time is important as well, and you need to take care of. And finally, this has been simulations experiment on the point-to-point Ethernet, so for 2 peers in MKA. And then I guess if you are interested in us rerunning experiments and simulation for 10BSD1S, let us know. We are happy to discuss that. And with that, I would like to conclude this talk and would like to open the floor for questions.
Thank you very much. Do we have any questions? Please feel free to come.
Harry Palmer from Infineon. Thank you for the presentation. I didn't come in time, but I saw the tail end of it. But the question at the end you had. So we're right in the middle at the moment in TC17. We had a meeting actually just a week ago, Friday, with a close collaboration with Heitmann from IEEE regarding the next phase in terms of MKA, and at the moment we're right in the middle of it. Please join us in that discussion because there is, from 10BSD1S, there is a need from them that they want to do rekeying. So please contribute because if we can find an argument, we've been trying to say that we don't need to do the rekeying, but at the moment I think it's a sort of he feels that it's a vulnerability issue, and let's maybe discuss that in that forum in the TC. But please,
for sure. So actually, my plan was also to present this in the TC17 before the tech day, but then time didn't allow it for me to prepare that. But we can definitely discuss this there as well. Sure. And yesterday, I actually remembered that I wanted to ask you what the discussion with Mick gave, and that I couldn't make it to that discussion, but for sure we can do so. Yeah.
So at the moment, I think there was a presentation that we had given at the plenary in July. This was kind of rebuffed by Mick, but we think we have a closer collaboration in terms of what parameters we can change. So I haven't organized the meeting. The TC17 meeting next Wednesday is planned, and or Thursday, I can't remember that. But if you can come and present this would be really good in that forum. Sure. Thank you.
Yep. Another question? Yeah.
Yes, one question. You say that this implementation is basically a profile of the IEEE MACsec version. Does it mean that it is fully compatible to the standard MACsec, or how do I have to judge this?
Do you want to answer, or should I take it?
I mean, your question is, what is the TC17 profile of MACsec?
Actually, I'm not involved in Open Alliance in TC17 at all.
Yeah.
So for me, well, I'm from Airbus, so I'm more on a general way rather than automotive only. So I'd like to understand, if I would like to use MACsec, what does it mean for me if I use also automotive components in conjunction with other components which also use MACsec?
So in general, the automotive profile is what we have until now, so not speaking about 10-base T1S, is fully compatible to normal IEEE MACsec. So they were also at the AEC in Munich, the Automotive Ethernet Congress in the last years. There were always interoperability plug fests, where basically automotive hardware was tested, and one part of that was, from my understanding, always a normal Linux implementation, an IEEE normal way of implementing MKA, and these optimizations that we are talking about here are basically playing with the timing, and they are not violating the behavior that the IEEE spec requires. Yeah?
Okay, I appreciate that, and I can follow the person which was asking before.
Yeah,
go standardize it and keep it in sync with the IEEE flavor. Yeah. Okay. Yes. Sorry.
The plan is to be compliant to IEEE, yes.
I appreciate that a lot.
Do we have another question? We have time for that. No? No other questions? So do not forget, if you have any more questions for this presentation or the presentations we have just gone before, you can use Speaker Corner in order to discuss directly with the presenters. So thank you very much.
Yep, thank you.
So,
Thank you.
So we are a little bit early, but we can take a break. So the next presentation will be at 3:30. So it's the occasion to go to the exhibition room and see you after the break.